Internet people, we meet once again for this, the fourth chapter of our S650 101 tuning class. Starting to see a little activity out there. Some people are starting to look at these, chat, and talk about them. A couple people have reached out to me, so it's been a minute since I put one out, and given that I'm getting a little bit of feedback, I am strongly encouraged and put this together today to keep the ball rolling. So, this material is near and dear to my heart. I really love the four-stroke cycle. I don't know why. I think it's because when I first was getting into cars, I was trying to understand what turbochargers were and why they were such a big deal. And I had never heard the famous two words, forced induction. And I started researching, and when I found out how forced induction works and how it augments the four-stroke cycle, I thought it was really neat. And it forever made me an addict of all things cars and tuning. So hopefully I can share some of that passion with you. Let's get going. Let's watch the mouse fail. Perfect. All right, so lesson plan today. What are we doing? We're going to look at what is the four-stroke cycle. We'll define it. Spoilers. Stroke 1 is an intake stroke. Stroke 2 is a compression stroke. Stroke 3 is a combustion stroke. And stroke 4 is exhaust. We're going to get into all those. I'm going to introduce the idea of something I call combustion differentials. Excuse me as I sip my coffee. And I'm going to look at the end at forced induction, like I was saying. So let's go. Let's do this. What is it? Four-stroke cycle. It's fundamental operation of the engine. You can think of it as the heartbeat. It is the activity that all other activities radiate from. Ultimately, the motion of the car, any of its operations, fundamentally comes down to this four-stroke cycle. The four-stroke cycle, just for trivia's sake, is for engines that have oil reservoirs separate from the fuel, and they run on just straight gas. If you are a homeowner or if you are a renter who is doing your own lawn and garden maintenance, you're probably aware that there are two-stroke engines. Those are engines that have the oil blended in with the fuel. So things like weed whackers, other little small engines. They're kind of fun to work on. And those are two strokes. This is for four strokes. This is for gasoline-powered internal combustion engines that have separate oil reservoirs. Air, fuel, spark, and exhaust are all managed throughout the cycle. Ultimately, if you are dealing with a problem with the car, it will come down to one of those four things. The crankshaft and the camshafts in the four-stroke cycle will rotate 720 degrees during the cycle. So the cycle has two full circles that each of those is going to go around. The crankshaft powering the pistons and rods and making power for sending through the powertrain and ultimately to the wheels. Camshafts are working alongside them perfectly in sync, and their lobes, as they rotate around, are controlling the tappets of the rods that then push down on the valves and control the breathing, right? So the core clockwork of the whole thing. The valve train, like I was saying, governs the precise timing of the air intake and exhaust, okay? So when I first started creating some of the materials to define this, I went through the four-stroke cycle and I kind of glossed over the valve train and I glossed over this idea of the 720-degree rotation. It really is critically important because later on when we start talking about things like injector duty cycle, spark timing advances, when we talk about the mapped points and the understanding the distance tables and distance to optimal power and all these things, right? You've got to have an understanding of what these camshafts are doing if you're going to be able to tune this car successfully, right? So I really harp on this idea, and I'm introducing this now. 720 degrees, two 360-degree circles, right? Because later on we're going to start referring to intake and exhaust angles and they reference a local angle. It's not like we say, okay, at the 540 degree mark, the intake valve opens. It's not quite how that works, but you do need to be aware that it's 720 full degrees in the cycle here. So just be aware. All right. There are 4 subcycles, like we said. There's the air and fuel intake, compression, spark and combustion, and exhaust. So let's get on the first one, intake. Okay, so we have over here an illustration of what is going on in a cylinder. This here is our good friend the crankshaft down low. These are the pistons. Ultimately, sorry, here. This is the piston. It's this flat surface here, so this is solid metal. It's got the rod underneath it, right, that is mounted to the crankshaft, and this goes wee around and around, again and again and again, okay? And the piston here, at the beginning of the cycle, is at something called top dead center, which would be the piston fully inserted into the cylinder here. And this space between the valves, this here is your intake valve, this here is your exhaust valve. When it's up at the top, it's as close to those as it can possibly be, and the cylinder is under the maximum compression. Okay, so we're fully inside this void, right, where it's, filling the cylinder. When the cycle begins, the crankshaft is already under momentum, right? And like the only time it's the special situation of when you're doing a cold start, where you have the crank and you need, it is not already in motion. That is where you have a solenoid that is the solenoid to rule all solenoids. If you know what it is, it's a coil of wire with like a rod in it, and as the electricity hits that wire, it magnifies, produces a field, and the rod will move back and forth. That's how cars start. We're not going to get into that. But it's the only time where it wouldn't already be in motion. Most of the time, this is already in motion, so the momentum of the crankshaft will send the cycle beginning, and the piston will begin withdrawing from the top of the cylinder. And when it does that, just like you use a straw in a drink or other conditions, you can produce a vacuum. Okay, and that's exactly what happens as the piston begins going down and a vacuum state is created within the cylinder, which is why the air pump ultimately led to internal combustion engines. That's a whole other topic. The camshaft lobe during this time will move over the intake valves. The lobe will hit the tappet, it'll hit the rod, and it'll activate, and the rockers will hit the rod. The whole assembly of the valve train will knock this piston or that intake valve down. And as it gets knocked down, these pathways open up and we can begin pulling air in from the intake manifold. Okay. And ultimately that is connected through piping to the air box, right? And it's all being measured by the MAF sensor, which we'll get into. But the air begins rushing in because of the vacuum state. You got to have it. And also because we're supplying the vacuum state its demand for matter, right? Gas, anything, by opening the valve. And that's the whole thing here, right? It breathes. Now, that's one half of the equation. The other half of the equation, there are injectors in here that are dumping an atomized mist of fuel right into the cylinder here along with the air. The pressure on these fuel rails, the upper fuel rails, is something like 2,000 psi. When you have that much pressure and you put it through that tiny hole of the injector with the duty cycle governing exactly how long we turn it on, it produces a mist of fuel. Gasoline, most people don't know this, when it's in its liquid state, doesn't like to burn. What are you talking about? It doesn't like to burn. Like if I just take, this is a stupid experiment, right? But if I take a match and I drop it into liquid gasoline that somehow I prevented from evaporating off, it won't light. It's the vapor, the aerosolized version of gasoline that ignites. You've got to either atomize it, right, or let the vapors accumulate. That's what's burning. It's in its gaseous state, right, not the liquid state. So that's why the injectors are doing the incredibly important job. And put the mist in the cylinder, right, and you're able to begin here. Okay, and so the other thing is that, the air is flowing. It's moving around in billowy little puffs and clouds. It's turbulent, right? And the fuel is also turbulent, and they are not mixed stoichiometrically. And we'll talk about what that means in a minute here. Just they're not quite. It's like cake batter, right? We put the flour in, we put the sugar, we put the eggs. They're all in there, haven't mixed yet. Okay, so now let's get to the mixing. Compression. Here we have our good friend, the crankshaft. We have the cylinder. We see the piston going up. It began at bottom dead center, which is the counterpoint to top dead center. After coming all the way down to do the intake, we're now bottom dead center, and the crankshaft goes around again. We begin pushing up. That begins to compress the air and the atomized fuel. And as they interact with one another, just by virtue of entropy and the universe, right, it begins to mix a little better. Also, because we're compressing it into a smaller space, it mixes a little better. The compression ratio for the S650 fourth generation Coyote is 12:1. So you're cramming the 12 things that were in the cylinder, right? The unit of volume is 12, and we're compressing that down to a unit of volume that is 1. Or rather, we're pushing all this into 1/12 the size of the cylinder. That is a hell of a lot of compression. Most cars, if I was to go find any sort of random Toyota Camry, something like I think 10 and a half, and that's pretty high, right, from cars back in the day. It's a testament to the quality of the metal ores and the refining we do and the machine work and the degree to which human civilization has progressed with metallurgy that we can compress this shit to 12:1. It's impressive, just calling it out. When that happens, so a couple things. The valves here are closed, both intake and exhaust, and that's why they have this conical shape, is because as pressure pushes on these discs of the valve, it naturally sort of seats it against the metal flush, forming a seal. So as this is compressed, we don't want this to leak. That's bad, right? And that's why sometimes you'll hear a mechanic say you need a leak down test, right, or a compression test to make sure that you are in fact hitting that 12:1, right? And maybe like 11.8, 11.9:1. Not good, but engineering is the study of the imperfect, right? And just keeping it running. But if you were to if you say, hey, you're supposed to be 12:1, you're only holding 8:1, you've got a leak, you've got a problem, there's something wrong, right? Something about your crankcase overall, it's a problem, a big one, right? Just to highlight here that air is not leaking, coming or going at this point, right? We're just squeezing the shit out of it. And at that point, okay, here's the good stuff. I like this stuff. Because of something called Boyle's Law, which says if I take a gas and I put it in a certain volume, so imagine I've got a 1-gallon jar and I open it and then I close it. Inside that 1-gallon jar will be air, right, from the Earth's surface. And that air will be at a pressure. And that pressure, I think, we call it 1 atmosphere. I think it's 14.5 psi, right? And that's just the blanket of air, that we breathe every day, just pressing on us, because it does press on you. That is equivalent to the number of units of what am I trying to say? Of molecules, basically, right? The amount of molecules of air that are in there, and then there's a constant, right, R, which we won't get into. Temperature, though, right? That volume of stuff at that temperature will equal this volume at this pressure. And what that means is that, and if that was mysterious to you, don't worry about it. What it means is that when I take a gas and I compress it, that gas will heat up. And I'm not talking a little bit. It will heat up dramatically, okay? So that happens when you pressurize this air and fuel. It does heat up. And the problem there is this is why we need high-octane fuel. Let me explain that. So high-octane fuel has molecules of hydrocarbons that are more knit together than low-octane fuels. The heptane content is higher. It is harder for Think of it like dominoes. Okay? If I set up a trail of dominoes, I know that I can tip one over and the whole thing will start going, right? And if I assume they're magic dominoes, and as they lean one way or the other, they don't fall over for whatever reason. Low octane would be sort of at a downhill angle, such that a slight bump of the first domino will set the whole chain reaction going quickly, right? Higher octane flattens that out, where it is a little harder to invoke the chain reaction, right? And, at the highest, that's like 93, 94. It's why we need to put premium gas in our S650s. And this is because the conditions are hotter in the cylinder, right? Heat makes fuel want to explode, right? So the hotter it is before the ignition point, the easier it is for detonation to happen. Detonation is unintended combustion. And what'll happen is, for whatever reason, let's say, for example, we got really aggressive with our watt lambda. We'll talk about later what that is. But I set my targets too high, and I'm running it too hot, and my tune was done in spring, and now it's July. And also, I've done a few other things that I'm increasing the power that I'm asking for from the engine. If you get too hot, and then you put in fuel that isn't high enough octane, it'll hit the cylinder walls and it will ignite without the spark plug going off. That's detonation. And if you are in the middle of this cycle, for example, if you are compressing, which increases the temperature, and that temperature gets high enough that in the middle of the compression stroke it ignites, it will then begin pushing against the motion of the crankshaft, and you will grenade your engine. That is knock. That is an engine killer, okay? And that is why we need high octane fuel, and that's why when you see cars that have massive superchargers or turbochargers that are pushing like 30 pounds of boost, it's why they're spraying methanol or using race gas, right? And we're going to keep talking about this. These are the consequences of understanding this cycle fully. That's why these fundamentals are the core of tuning, because if you don't understand these dynamics, you won't be able to troubleshoot and problem solve later on. Okay, and detonation is the number one enemy, right? In all things, as tuners, we want to absolutely ensure we are not going to have a detonation. Okay, enough doom and gloom. The fun part, the combustion cycle. So, returning to the idea of the piston being at top dead center. During the combustion cycle, this mysterious jacket of gases and fuel has been compressed to its most compressed state. The spark plug fires at the intended time, and when that happens, the combustion cycle begins. And the spark will ignite the mix. Hopefully the mix is stoichiometric. Now, what does that mean? If you haven't heard of stoichiometry before, the idea here is that the amount of air molecules compared to the fuel molecules is at a golden ratio where all of the oxygen is consumed and all of the fuel is consumed. I don't have anything left over. With gasoline that has no ethanol added, it takes 14.7 molecules of oxygen to match 1 molecule of gasoline. You put the two together, you put the conditions together properly for the pressure and all that, and you ignite it, and they will both burn off clean, essentially leaving no residues behind, right? It's not quite true, but we'll say that for now. When that happens, and we have everything balanced, which is the whole other point of tuning and fueling calibration, is we are hitting this stoichiometric goal. When that happens and you have a clean burn, there is a flame front that begins forming in the cylinder, and that flame front travels across the volume of the cylinder in a glorious display of power, and it pushes the crankshaft down. It is the net power gain from the whole cycle. It is the purpose. It is why we do this, right? That pushes the crankshaft down, making the horsepower, and we go, wee. Okay. During this event, the valves are still closed because we don't want to throw off the reaction. We don't want to be exhausting yet because we might lose power. We don't want to be intaking air because then the whole point here of the stoichiometric mix being properly mixed. If we start adding or subtracting air, it throws that off. So we don't want to do that, right? We keep it all sealed up. And at the end of this, we have the byproducts of combustion, exhaust, the spent fuel, right? So the oxygen burns, but that doesn't mean like the nitrogen and those other components are burned, right? They're just really hot now, right? And we're talking 1300 Fahrenheit, maybe hotter if something's wrong, right? But those kinds of temps, if there is fuel left over, so let's say across the board I had for each 14.7 molecules, instead of having one of air, oxygen, what if I only had what if I had 1.2 molecules of gasoline across the board on average, right? That means I'm going to have a little bit of gas left over. And that means that I'm running rich. I have commanded the computer to put too much fuel into the cylinder. I have unburned fuel, right? And that's bad because we're leaving some power on the table. The catalytic converter has to deal with it as a consequence. Probably the only good thing about it is that fuel does have a bit of a cooling effect, but it's not at a point where we can use it. And we're talking about that more later, right? Conversely, if I had one set or one molecule of gasoline and I need 14.7 of oxygen, but I only have 13, right? Now I have starved myself of air, right? And if I had had that air, I could have burned that fuel, right? I think I got that right. I have to double check. Not enough fuel though, right? And too much air at the end, that if there's oxygen left in the combustion chamber, and the oxygen sensor will sense it in the catalytic converter, we'll get to that in a sec, that means you're running lean. And lean makes things real hot, right? You got to know this later on, right? If we go lean, it's a real problem. Better to be rich than lean, which is why if you are trying to settle in on a calibration target, I would rather be a little bit above too rich than a little bit below, because at least too rich, it's a problem, but I'm not going to be increasing heat in the cylinder. Lean, I'm increasing heat. And what does heat do? Leads to detonation. Bad. All right, final step here, exhaust. So we look over here at my friend. The intake valve stays closed. I've got my hot gases rolling around in here. I'm going to open my exhaust valve, and I am going to have the cylinder begin going back into the, or the piston rather, going back into the cylinder. Okay. As it begins to enter the cylinder, the valve opens, and as it pushes, right, as it goes up, it forces the gas out, because given the option, a gas doesn't want to be compressed, right? It would rather exit, right? So that's the whole point of the exhaust cycle. And when that happens, it'll leave via the headers, and the headers lead immediately to the catalytic converter. And the catalytic converter, I think I have that next here, right, is an interesting aspect to this whole thing, because I'll present two sides to it. So when you're sending these byproducts out, they hit the catalytic converter, they're incredibly hot, and the catalytic converter itself, by design, heats up, right? It's meant to handle these high temperatures. As the hydrocarbons enter it, right, and these are the kind that pollute the environment, and they contribute significantly to global warming. The catalytic converter scrubs them. It, catalysis, I guess what you call it. The whole catalytic means I'm turning it from one thing into another, right? Transmogrifying, if you want to be mystical about it, right? But it takes the nasty, smelly hydrocarbons that pollute the environment, and it converts them over to a form that is not as harmful, not as smelly, good stuff, right? That's the good part about this thing. And there is an oxygen sensor before the catalytic converter that will read how much oxygen is in the exhaust. If there is oxygen present, that means we know we're running lean. right? Or if there's not as much oxygen as we expect. Conversely, if it's all gone, right, we know we might be in a rich state. So the oxygen sensor will tell us that. There's one before the catalytic converter, and then there's one after the catalytic converter. And it's like it does a check. Like, is everything running right? Is the cat running right? All's good, right? And it measures all things again, and also the temperatures, I believe, right? There's a purpose to it for the whole thing to run properly. That then goes out the tailpipe all as well. The problem with a catalytic converter is that by design, because it's a filter, it produces back pressure, and it resists the airflow out of the engine in through and out the car, right? And if we remove it, if we just simply remove it, we remove that back pressure, and air flows better. And where you have more air, you can have more fuel. And where you have more air and fuel, you have more power. Okay? So a lot of people, of course, say, fuck my catalytic converter. No, this is a no-brainer. And you put in something called a straight pipe or a race pipe or whatever you want to call it. You guys all know what I'm talking about, right? And that's all fine and well until one day you come across the emissions man, and you have to do your daily, your yearly inspection rather, and up it goes on the rack. And if you don't pass, you got problems, right? It can lead to all sorts of silly government troubles, right? So there's ways around this. One of them is you run around with a race pipe the whole most part of the year, and just like if you've got a tint that is illegal, once a year you take all the tint off and pay the tint man, and you go to the shop and pay the exhaust man, and you put it all together so you can pass the test. You go back and take it all apart again, and you go your merry way, right? I don't want to do that. I don't have time for that. I work for a living. I'm not taking this to the racetrack. I'm not taking this to the drag strip looking for 0.2 of a second, right? So I go with option B. And option B is if you can use your catalytic converter that comes with the car. If you're doing stock, if you're light power adders, it's not going to be a problem, right? The problem begins with things like long tube headers. And if you put long tube headers on, it will increase airflow overall. We'll talk about that more later. But if there isn't room for that second oxygen sensor, guess what? You get to check engine light, because it's not able to monitor the whole process here and make sure that everything is running right. And that's where you have to go in and get rid of the code or figure out a workaround, right? And then the other problem is that we'll talk about the other problem later. We'll keep moving on for now. Just remember, catalytic converters. Okay. Combustion differentials. A differential apologies, mild disruption. A differential is something that is in a changing state. That's all it means, right? And so let me bring up the table so this isn't mysterious. You want to be thinking about the four-stroke cycle and all the things that are happening as events that are constantly on the move, right? And there's different portions of it doing different things. It's dynamic. It's constantly in a changing state, right? And some of the dynamics you want to think about here, if we think about the cycle here and the different... go back. If you think about these four components to the cycle, during the intake, for example, the cylinder is experiencing a cooling effect. Air is coming into the cylinder. Even better, though, gasoline as a mist is coming into the cylinder. And like I was saying, gas doesn't ignite right away. It takes a good effort to get the chain reaction to begin happening. Gasoline itself has a remarkably cooling effect on the cylinder, right? And that cooling effect is a massive benefit if we're trying to calm things down, make sure we don't get detonation. It is in fact a high cooling effect. It is the most cooling there is for the cylinder. The intake is in a state where the vacuum is being filled. So there is a vacuum state that's beginning to happen. But we're filling it with air and we're filling it with fuel. So even though we're creating a void, we're able to fill that void. And then the headers, we're going to use the term phase blocked. And you see I even have an asterisk here, so there's a lot to talk about. For now, just understand that the valve train has phasers that are adjusting the functioning of the valve train. And in this moment, during the intake stroke, those phasers are closing the exhaust valve. So it is blocked, right? So that valve is phase blocked. We'll come back to that. During compression, though, the cylinder is beginning to heat up simply because of compression. But we don't have a flame front yet, so we're only heating up a little bit. Our intake at this point with that valve closed is phase blocked, like this one was. And this one is still phase blocked. Remember, those valves are closed. During the combustion cycle, obviously the cylinder has a massive heating event. It is the high heating event. And again, these are still phase blocked. And then in the exhaust, we have some cooling in the cylinder just because we're ejecting the hot gases, but it's not a lot. It's not at all like the intake stroke with that lovely mist of liquid that collects on the walls of the cylinder and cools things right down. In the intake, we are pushing the exhausts out, and so we're getting ready to form a vacuum. It's really the only way I could describe it. And of course, the headers, we're beginning to heat those up. Okay. Now, what is the asterisk? The asterisk refers to something called blow-through, which is not something we really have to worry about on the Mustang S650. That is coming straight from Eric and other good folks over there at HP Tuners. Thank you so much, guys, for all the work you do. There are times where, for whatever reason, my exhaust valve might be just a little bit open still while my intakes opens. And for a brief second, they might simultaneously be open. And that's where any air I'm pushing in is filling the cylinder, but it could be leaking out through the exhaust valve. That's blow-through, right? And sometimes it's something you have to account for. If you're producing a ghost tune, you need to know all about this, and I'll just leave that there for now. But that's all that is. Okay, the really good stuff now. Forced induction. What is it? Leverages an already functioning engine to power an induction device for a net positive power gain. Okay. Basically, what we want to do is, instead of relying on the vacuum state to draw air into the engine with natural aspiration, a naturally aspirated engine, we want to cram fucking air down its throat. And we want to pressurize the crankcase because we know our seals are up to the task. We know that the engine is running right. We know that we don't have any leaks or blow-by or any other problems. So we don't mind just doubling the pressure inside that crankcase because with the extra air, extra oxygen, extra fuel, and of course that means more power, right? So there's two ways to do this, two major schools of thought. The supercharger. It's a belt-driven device, it's powered by the crankshaft, and it is a parasitic draw. Okay? And the first one, for example, is the positive displacement supercharger. This is like the one from Mad Max. This is the amazing one. Just looks so cool, right? And it has these, it is not the twin lobe design, I forget the exact name right now, because I'm tired. But it's basically a giant compressor, okay? These lobes move and spin, and they produce pressure. They are compressing air. Now, remember what I just said. We just talked at great length. What happens when you compress air? It heats up. That's why the air has to move through this. It looks like a radiator. Radiators emit heat, right? So I take this hot air, I cram it through this radiator, which is called an intercooler, and the heat drives off into the atmosphere, right? Floods my engine bay. But the air will then come down into the runners of the intake manifold, right? And this basically, you take your intake manifold off and you put the supercharger on, and it has runners, and the air goes into the cylinder, except instead of it being drawn through naturally like a straw or a snorkel, we are blowing air in with this pump, right? And the con to the supercharger, of course, there's a couple. It produces a lot of heat. It's big, it's heavy, and the parasitic draw, as it pulls on your crankshaft, remember, like I said, the accessory, like an air conditioner, will rob the engine of power. These big superchargers I hear are something like 50, 75 horsepower that you lose to power the compressor. But of course, what do you gain? With that air blowing in and doubling the pressure, we can double the fuel, and we get a big, big gain, right? So for the cost of 50 horsepower taken away, the compressor's putting in like 350 horsepower, right? And as you decrease the size of the pulley that is attached to your crankshaft assembly, right? This compressor spins even faster, more compression, right? And we're really off to the races here, right? So the analogy here, if you're coming from the PC world, is this is overclocking, right? We're going faster than we originally intended by the engineer, but we can handle it because we know what we're doing and we've thought about this, right? And we've accounted for all the problems this is going to create. We'll talk more about that more in a sec. Okay, the second major kind is the centrifugal supercharger, which is this little bad Larry down here. It is also belt driven, but there's a big difference because this is driven by a pulley. It's a function of the RPM of the engine. So when you're at 3,000 RPM, you're not spinning this centrifugal supercharger as fast as when you hit 4,000, 5,000 RPM. Kind of similar to the turbo, but it's belt driven. So you don't get all the power all the time, right? You got to wind the engine up to begin drawing maximum power out of this thing. This positive displacement supercharger, did I call it that anywhere? I guess I didn't. This positive displacement supercharger, right? Write that in your copybook. This produces the power across the entire power band. And so for something like the S650 Mustang, which the torque down low is a little lacking and a little low, especially compared to our LT cousins, excuse me, another coffee sip, this device is a miracle, right? Because it will give you massive torque down low. No waiting, right? Now that's awesome. The problem, of course, is that you've now significantly increased the stresses on your crankshaft and at lower RPMs, which can lead to bogging and other stresses, right? And pointing out, you don't want to snap your crankshaft. Okay, there are limits to this. And the big limiting factor, though, is heat, which we'll talk about again in a sec. There you go. Both of these radically increase heat, which is why intercoolers are so important, right? We compress the gases, we run them through a radiator to cool them down, and then as they expand and enter the cylinder, they're cool and ready to use, right? It's the exact same principle as air conditioning, really. Okay, the other option, the turbocharger. The wonder snail, right? Just like a centrifugal, this is attached to the plumbing of the car. As the exhaust gases flow out of the header, right, it comes into a collector, right, that collects and spins this turbocharger. So as the gases go by the turbine is connected via rod to an impeller. This is the impeller. Okay, and that impeller begins spinning, and an impeller is like a propeller. It just goes in the other direction, right? And it sucks air into the engine. And again, we're hitting like double atmosphere, triple atmosphere, right? So if the regular, 30 pounds of boost is like 2 atmospheres above the existing atmosphere. It's a lot of air that you're cramming into the engine. Like a centrifugal, though, the turbo needs to spool up. It needs to spin up if it's going to hit maximum airflow hitting into the engine. And you will tend to set a boost target with the ECU, and the wastegate will open up, and when it hits, so for example, on my Mazda Speed 3, the stock was 15 pounds of boost. I had it at one point running up at 23, which was pretty cool because it was the stock turbo and I was spraying methanol. The wastegate, when you hit 23, is what opens and keeps you from having a runaway turbo event where you spin up to surge, where you go up to 25, 28 psi, right, which can screw the turbo, can break all kinds of things. So that's how it's governed. And then when you suddenly let off the gas, there's all this pressurized air in the system, and that goes out a bypass or blow-off valve. And so the famous noise for a turbocharger is the psh, right? You'll hear a rev and then psh as that air goes out. The supercharger, as you activate it, has a whine, right? And I fucking love that sound. But that's what's happening. Like superchargers, we're pressurizing air, and that's why we have increases in temperature, which is why intercoolers are so vital. Okay, so I'll leave a little tidbit here. For both of these, the higher temperature air needs to be accounted for throughout the tune. What does that mean? So we're going to look at fuel ratios next time. You remember I was saying I need like 14.7 molecules of air for one molecule, or oxygen rather, for one molecule of gas. With ethanol, 10%, we know that it's actually about 14.0 or 14.1. And so when we're doing regular driving, we command a target, an air to fuel ratio of about 14 to 1. Now, when we start getting on the pedal, though, and we ask for more power, that means we get more air, more fuel, more combustion, pressure in the cylinder, and heat, right? So when we start making power, we get heat as a byproduct. Heat leads to detonation, which is why when we're at partial throttle, we want to give it a little bit extra gas. We're going to deliberately enter a rich state where we're going to burn as much as we can, but we're going to leave a little gas behind. Why? Because it cools things, okay? And it prevents detonation. Over time, as the four-stroke cycle is used in a power run, right? So if you start a wide open throttle even, right? And that period of say 7 seconds where you're accelerating like a madman, that is a wide universe in the car world. That is like, this four-stroke cycle will happen thousands, hundreds of times, thousands, right? But it'll happen hundreds of times, right? And over the lifetime of those events, the temperature overall is going to go up and up and up and up, right? And if you begin getting into the world of forced induction, your cylinder temps are going to go up dramatically. The opportunity for detonation increases dramatically. And so where at wide open throttle, normally you would command something like 12.5 molecules of oxygen to the gas, with something that is supercharged, for example, you want to drop that down to like 11.4, which leaves a lot of fuel behind. And the reason we do that is because it helps keep the cylinder cool and it prevents the detonation and knock, right? That's why understanding all this stuff is so vital. So we're going to talk more about that. I know I keep saying that. We will. All right, coming up, other things we're going to do. So next time we're going to get really into this idea of AFRs. We're going to talk about the importance of lambda, why lambda is what you should be using. I had to go through this. I was comfortable with AFRs, and then somebody said, you're a jerk. You need to be telling me things in lambda. Right, so we'll understand what all that is, right? And then what fuel trims are. And I think we're going to embed the concept of closed and open loop operation in that conversation. We're going to talk in that conversation about the MAF and the mass airflow sensor and the vitalness of the mass airflow sensor. The session following, we're going to talk about speed density. And prick your ears up because this is super important for the S650s. What it is, what it does, volumetric efficiency, all that. I just said I might embed it. I probably will, so ignore that. Then, exciting stuff, we're going to get to the high degree of freedom execution model. It's the way, it's the ghost in the machine of Ford running your engine and ECU, and how it moves through the various cam states, and seamlessly moves through the conditions of idle, cruising, fuel economy, partial throttle, wide open throttle, limp mode, right? All and how it moves through all of those, right? Good to understand. That's the good stuff. Maybe a little boring for some of you, but it's good to know. Then we're gonna get into it, and we're gonna start doing the practical workshops of how to tune the MAF. We'll do in the basic workflow presentation, and we'll tune our MAF, and then from there we'll begin getting into speed density part 1 with a specific discussion of volumetric efficiency. Which, if you get scared of volumetric efficiency, we're just talking about fueling targets, and I'll explain what I mean when we get there. So that is it. Go forth, and happy tuning.